For most of human history, the moon has been the most dependable presence in the night sky. It rises, it fades, it returns. Civilizations have come and gone beneath it, coastlines have shifted, species have vanished, yet the moon keeps its rhythm with a patience that feels almost deliberate. Because of that reliability, it's easy to forget a simple truth: the moon is not fixed. It is moving. It always has been. Even now, the moon is slowly drifting away from Earth, widening its orbit by a few centimeters each year. This isn't theory or metaphor. It's measured with astonishing precision using laser reflectors placed on the lunar surface decades ago. The cause is a quiet exchange of energy. Earth's rotation pulls ocean tides slightly ahead of the moon, and that tiny lead transfers momentum outward. Earth spins a little more slowly. The moon climbs a little higher. It's a slow, graceful trade, unfolding over millions of years, and for life on Earth, it has been mercifully stable. But stability is not the same thing as permanence. An orbit isn't a rigid path etched into space. It's a balance, an ongoing negotiation between gravity pulling inward and velocity trying to escape. As long as those forces remain in harmony, the dance continues. If they don't, the dance changes. Sometimes by a whisper, sometimes by a collapse. To significantly alter the moon's orbit requires staggering amounts of energy. No earthquake, no volcanic eruption, no weapon humanity could build comes close. That fact feels reassuring until you remember that the universe is fluent in extremes. Space doesn't need to be malicious to be disruptive. It only needs to be indifferent. The moon's danger in this context comes not from what it might do to us directly, but from how deeply it is woven into Earth's systems. It steadies the planet's axial tilt, moderates the oceans, and quietly shapes atmospheric patterns. Life evolved under its influence, and human societies unconsciously synchronize themselves to its cycles. The moon isn't just overhead, it's structural. Change its orbit, even slightly, and those structures begin to strain. If the moon were drawn closer, tidal forces would surge far beyond anything recorded in human history. Tides don't rise gently with distance, they intensify dramatically. Coastlines would be battered by relentless flooding. Fault lines would feel new pressures. The planet itself would flex in unfamiliar ways. None of this would arrive as a single catastrophic moment. It would come as a grinding, rhythmic violence that never quite stops. If the moon drifted farther away, the danger would be quieter, but no less profound. Tides would weaken. Ocean mixing would slow. Nutrient cycles that support marine life would falter. Climate systems, long tuned to lunar rhythms, would begin to slip out of alignment. The world wouldn't end overnight. It would unravel gradually, one system losing efficiency, then resilience, then coherence. More unsettling still are the unstable possibilities. An orbit doesn't need to collapse to become dangerous. It can stretch, wobble, or resonate in ways that feed back into Earth's rotation and internal stresses. These are not disasters you can film in real time. They are the kind that show up as rising insurance maps, migrating coastlines, and weather patterns that no longer repeat themselves. Long before science put equations to these ideas, cultures sensed the moon's importance. Ancient stories rarely treated it as a passive ornament. It was stolen, wounded, chased, threatened. Eclipses inspired fear, not because of the darkness, but because they suggested interruption, cosmic order slipping, even briefly. Without understanding the mechanics, people understood the risk. Modern science confirms what those instincts hinted at. The moon is a stabilizer that looks harmless only because it has always behaved itself. Alter that behavior, and Earth becomes a more volatile place almost immediately. In the next segment, we'll step beyond this quiet foundation and examine how such a disruption could actually begin, how forces far beyond Earth, without ever touching our planet, could bend the moon's path just enough to set everything else in motion. The most unsettling way to change the moon's orbit is also the quietest. No impact, no explosion, No warning flare in the sky. Just gravity doing what it always does, reaching out across distance, bending trajectories, and altering futures without ever making contact. Space is not empty in the way it feels empty, is structured by motion. Stars orbit galactic centers. Planets drift through long, looping paths. Dark, cold objects, failed stars, rogue planets, dense clusters of mass, move invisibly between systems. Most of the time, these motions are far enough away to be irrelevant. But every so often, something passes close enough to matter. If a massive object were to drift through the outer reaches of the Earth-Moon system, it wouldn't need to collide with anything to cause damage. Gravity works at a distance, and the Earth-Moon relationship is delicate. The Moon is bound to Earth, but only loosely compared to how tightly Earth is bound to the Sun. That means the Moon is especially sensitive to outside interference. Imagine a large rogue planet, cold, dark, perhaps no larger than Neptune, passing through the solar neighborhood. It wouldn't announce itself with light or heat. For most of its approach, it would be functionally invisible. But as it moved closer, its gravity would begin to tug unevenly on everything nearby. Earth and Moon would not feel that pull equally. Their different masses and positions would cause subtle distortions in their shared orbit. At first, nothing dramatic would happen. The Moon might arrive a fraction of a second early or late. Its distance might vary by an amount too small for the naked eye to detect. But orbits remember disturbances. Once nudged, they don't simply reset. They evolve. A passing object could stretch the Moon's orbit into a more pronounced ellipse, bringing it closer at perigee and farther at apogee. That alone would be enough to destabilize Earth's tides. Each close approach would amplify tidal forces. Each distant swing would weaken them. The result wouldn't be a single catastrophic flood, but a planet subjected to rhythmic stress, oceans sloshing harder, then retreating farther, over and over again. If the passing mass were large enough, the consequences could escalate. The Moon might be nudged into a resonance with Earth's rotation, a feedback loop where tidal forces begin to reinforce the orbital distortion rather than dampen it. Once that happens, the system no longer corrects itself. It drifts toward instability. The truly dangerous scenarios aren't the dramatic flybys that rip moons away or send planets spiraling into stars. Those are rare and obvious. The dangerous ones are near misses, close enough to perturb, far enough to leave everything apparently intact. From the surface of Earth, the Moon would still be there. It would still rise and set, but it would no longer behave quite the same way twice. Earth itself would feel the change internally. Tidal forces don't just move oceans, they flex the planet's crust and mantle. An altered lunar orbit would redistribute stress along fault lines that evolved under very specific conditions. Earthquakes wouldn't need to become more powerful to become more frequent. Volcanic systems could shift as magma chambers respond to new pressure rhythms. Even Earth's rotation, already slowing, could wobble enough to subtly affect climate zones. From a human perspective, this would be an apocalypse without a beginning. There would be no single date to circle on a calendar. Instead, there would be a growing sense that the old patterns no longer apply. Tides would stop matching charts. Coastal flooding would become unpredictable. Weather systems would drift out of phase with seasons people thought they understood. Ancient cultures imagined the sky as fragile for a reason. They told stories of wandering stars and stolen moons because they sensed that order depended on distance and timing. Modern astronomy doesn't dismiss those fears, it refines them. We now know that the solar system has experienced close encounters before, especially in its early history, when stars formed in dense clusters and gravitational chaos was common. We also know that such encounters become less likely over time, but never impossible. What makes this possibility so unsettling is that it requires no violence, no collision, no obvious trigger. Just a silent passerby, moving through the dark, close enough to whisper to the Moon, and change everything that depends on it. In the next segment, we'll turn inward and explore a more immediate and tangible threat: how a massive impact within the Earth, moon system itself could abruptly rewrite lunar motion, and why even a single strike in the wrong place could echo across the planet for centuries. Not all orbital changes arrive from afar. Some begin violently close, with no subtlety at all. A single impact, if large enough and placed just right, could alter the moon's motion in ways that would echo across Earth for generations. The moon still carries the scars of its past. Its surface is a record of catastrophe, written in craters and frozen lava seas. Many of those impacts occurred billions of years ago, when the solar system was young and crowded. Back then, collisions were common. Today, they are rare, but rarity does not mean irrelevance. An impact capable of changing the moon's orbit would need to be enormous. Not the kind of asteroid that devastates a region, or even the kind that ends a geological era on Earth. It would need to be large enough to meaningfully alter the moon's momentum or redistribute its mass in a way that gravity could no longer ignore. Such an impact would not need to knock the moon out of orbit entirely. It wouldn't need to shatter it or send fragments raining down on Earth. In fact, the most dangerous outcome would be far more restrained. A glancing blow, an oblique collision, could slightly change the moon's velocity or tilt its orbital plane just enough to matter. Momentum is unforgiving. When it changes, it doesn't ask whether the system is ready. If a massive object struck the moon off-center, the energy would be absorbed unevenly. Shock waves would ripple through the lunar interior, potentially shifting dense regions beneath the crust. The moon's center of mass could move, subtly but decisively. Once that happens, gravity rewrites the rules. Earth would begin pulling on a moon that is no longer balanced the way it used to be. From Earth's surface, the impact itself might be visible, perhaps even spectacular. A sudden flash on the moon, followed by a new, slowly expanding scar. But the true consequences would not reveal themselves immediately. They would unfold in motion. The moon's orbit might become slightly more eccentric, its distance from Earth varying more dramatically from month to month. Or its inclination could change, altering where and how eclipses occur. These shifts might sound cosmetic, but they are not. They change how gravitational forces are distributed across Earth's oceans and crust. Tides would begin to arrive out of sync. Some coastlines would experience higher extremes, others strange lulls. River deltas, already fragile, would erode faster. Coral systems tuned to narrow tidal ranges would struggle to adapt. Over time, the planet's equilibrium would drift. Earth itself could absorb part of the shock indirectly. The moon acts as a brake on Earth's rotation, stabilizing the length of the day and the tilt of the planet's axis. An altered lunar orbit could weaken that stabilizing effect. Over long periods, Earth's axial tilt might begin to wander more freely, pushing climate zones toward extremes. Winters would grow harsher in some regions, summers more punishing in others. What makes this scenario especially unsettling is its asymmetry. Earth would not be struck. Humanity would not feel the blow directly. Instead, we would live downstream of it, inhabiting a system that had been quietly destabilized by a single event long past, visible only as a pale scar on the moon's face. Cultures have long imagined the moon as something that could be wounded. Myths speak of cracked moons, bleeding moons, moons struck by divine punishment. These stories weren't scientific, but they were perceptive. They recognized that damage to the moon would not stay on the moon. Modern science agrees. The Earth-Moon system is not resilient in the way we like to imagine. It is stable, yes, but stability is conditional. It depends on balanced symmetry and history continuing uninterrupted. Break that continuity with one well-placed impact, and the consequences don't end when the dust settles. In the next segment, we'll examine a slower, more insidious possibility: how changes originating on Earth itself, deep within its interior or oceans, could feed back into the moon's orbit over time, turning our own planet into an unwitting participant in lunar destabilization. It's tempting to imagine the moon as something acted upon, never something that responds. A passive companion shaped by forces beyond Earth. But the truth is more uncomfortable. The Earth and Moon are locked together in a gravitational conversation, and Earth speaks just as loudly. The Moon's orbit is not governed by lunar mass alone. It is shaped continuously by Earth's rotation, its oceans, its internal structure, and even the distribution of its continents. Change Earth enough, and the Moon responds. We already see this happening in slow motion. Earth's rotation is gradually slowing, not because of friction in space, but because of the oceans. Tides raised by the Moon slosh against continental shelves, dissipating energy as heat. That lost rotational energy doesn't vanish. It is transferred to the Moon, pushing it outward. This process has been steady for hundreds of millions of years, but there is no rule that says it must remain steady forever. Earth has not always looked the way it does now. Continents assemble and break apart. Supercontinents rise and fracture. Ocean basins open and close. Each rearrangement subtly alters how tidal energy is absorbed and redistributed. At certain moments in deep time, tides were far more powerful than they are today, not because the Moon was closer, but because Earth's geography amplified them. If Earth were to undergo a major internal restructuring through accelerated mantle convection, large-scale tectonic reorganization, or rapid sea level redistribution, the tidal balance could shift dramatically. The Moon would feel that shift as a change in how efficiently energy is transferred from Earth's spin into its orbit. This is not a fast apocalypse. It is a slow betrayal of equilibrium. Imagine a future where melting ice caps raise sea levels enough to flood continental shelves on a global scale. Shallow seas are excellent at dissipating tidal energy. Flood them, and the braking force on Earth's rotation increases. Earth slows faster. The Moon moves outward more quickly. The change might still be measured in centimeters per year, but compounded over centuries, it could begin to matter. Now imagine a more extreme scenario. A period of heightened volcanism reshapes ocean basins. Massive lava flows alter seafloor topography. New shallow regions appear where deep water once dominated. Tides become more chaotic, less predictable, more energy-hungry. Earth loses rotational energy at an accelerated rate. The Moon doesn't resist this. It accepts the energy and adjusts accordingly. At first, the changes would seem benign. Days would grow microscopically longer. The Moon would appear just slightly smaller in the sky over generations. But the stabilizing influence of the Moon on Earth's axial tilt would weaken. Without that steady anchor, Earth's tilt could begin to wander more freely under the influence of other planets, particularly the massive pull of Jupiter. Axial instability is not dramatic in the short term. It doesn't topple cities or flood continents overnight. Instead, it reshapes climate zones. Deserts drift. Ice caps migrate. Regions that once supported agriculture slip into marginality. Civilization doesn't collapse all at once. It thins, fragments, retreats. What makes this possibility so unsettling is that it doesn't require an external enemy. No asteroid, no rogue planet. Just Earth doing what it has always done, but faster or differently than life and civilization are prepared for. Ancient cultures sense this connection intuitively. The Moon governed calendars, tides, fertility, and time itself. It was never separate from Earth. It was part of a single system. Disturb one, and the other responds. Modern science confirms that intuition with equations and simulations. The Earth-Moon system is a feedback loop. Stable but not immutable. Self-correcting, but only within limits. If Earth crosses those limits, through climate-driven sea level change, tectonic rearrangement, or internal energy release, the Moon's orbit will not remain what it was. In the next segment, we'll push this idea further, exploring what happens when multiple small changes begin to synchronize, how resonance, rather than raw force, can quietly transform a stable orbit into a destabilizing one, and why resonance is one of the most dangerous concepts in celestial mechanics. The most dangerous changes in orbital systems rarely come from brute force. They come from timing. In physics, resonance is what happens when small, repeated nudges arrive at just the right moment. Each push is modest on its own, but together they accumulate, reinforcing one another instead of canceling out. A child pumping their legs on a swing doesn't need to kick hard, only consistently and in rhythm. Celestial systems behave the same way. The Earth-Moon system is already full of rhythms. Earth spins. The Moon orbits. The oceans rise and fall. The planet flexes ever so slightly under tidal strain. Most of the time, these motions are out of sync just enough to keep things stable. Energy is transferred, but not explosively. Balance is maintained. Resonance begins when that balance slips. If the Moon's orbit were altered slightly by a passing mass, an impact, or gradual changes on Earth itself, the timing between Earth's rotation and the Moon's motion could begin to align in new ways. Tidal forces might start reinforcing orbital eccentricity instead of smoothing it out. Each close approach of the Moon would strengthen the next one. Each retreat would make the return more extreme. This doesn't look dramatic at first. The Moon still follows the same general path. It still rises and sets. But its distance begins to vary more sharply. Perigees become closer. Apogees stretch farther out. The orbit breathes unevenly. Tidal forces respond brutally to distance. When the Moon swings closer, Earth feels it immediately. Oceans surge higher than predicted. Coastal flooding becomes less predictable, more localized, more violent. When the Moon retreats, tides weaken abruptly, disrupting estuaries and marine cycles that rely on regular mixing. The real danger is feedback. Stronger tides dissipate more energy. More energy loss from Earth's rotation means more momentum transferred to the Moon. That momentum doesn't necessarily stabilize the orbit. It can exaggerate its distortion if the timing is right. The system begins feeding its own instability. Earth's interior responds as well. Tidal flexing isn't confined to water. The crust and mantle deform slightly under lunar gravity. Change the rhythm of that deformation, and stress redistributes. Fault systems that evolved under predictable cycles begin experiencing irregular loading. Earthquakes don't need to be stronger to be more damaging. They only need to arrive out of sequence. Over decades, patterns humanity depends on would quietly break down. Tide tables would lose reliability. Coastal infrastructure would be designed for averages that no longer exist. Insurance models would fail before the coastlines themselves do. Agriculture near deltas would suffer as saltwater intrusion accelerates and freshwater flows become erratic. What makes resonance especially insidious is that it hides behind familiarity. Nothing new appears in the sky. No foreign object announces itself. The Moon looks the same until people notice that it sometimes looks slightly larger, sometimes slightly smaller, and no one can quite agree on why the tides feel wrong. Ancient myths often warned against disturbing cosmic rhythms, not because they feared chaos in the abstract, but because they understood cycles. The idea of keeping time was sacred because time itself was seen as fragile. A missed beat mattered. Modern orbital mechanics tells the same story in different language. Resonance is not an explosion, it is a runaway echo. Once established, it is difficult to stop. Systems either settle into a new, harsher equilibrium, or they continue amplifying until something breaks. In the Earth-Moon system, what breaks wouldn't be the orbit itself, at least not at first. It would be the environments and societies adapted to the old rhythm. In the next segment, we'll examine what happens when the Moon's stabilizing grip on Earth weakens further, how axial tilt begins to wander, seasons lose their predictability, and the apocalypse shifts from coastlines to climate itself. One of the Moon's most important roles is also one of its least visible. Beyond tides and calendars, the Moon acts as a stabilizing weight on Earth's axis, damping the planet's natural tendency to wobble under the gravitational influence of the Sun and the other planets. Without the Moon, Earth's tilt would be far less restrained, drifting chaotically over long periods of time. With it, the tilt remains remarkably steady. That steadiness is not guaranteed. If the moon's orbit were altered, pushed farther away, stretched into an unstable ellipse, or weakened through resonance, its stabilizing influence would diminish. Earth would still spin. The seasons would still exist. But the quiet anchor that keeps them familiar would loosen. Axial tilt determines how sunlight is distributed across the planet. It defines seasons, climate zones, and the boundaries between ice and water. Even small changes matter. A shift of just a few degrees can mean the difference between permanent ice sheets and open oceans at high latitudes. As the moon's grip weakens, Earth becomes more sensitive to gravitational nudges from other planets, especially the massive pull of Jupiter. Over thousands of years, Earth's axis could begin to wander more freely, swinging through wider angles than life and civilization evolved to handle. The changes would not be smooth. They would lurch. Some regions would experience brutally intensified seasons. Summers would grow hotter, winters colder. Snowlines would migrate. Croplands carefully optimized for historical climate ranges would fail. Other regions might lose seasons almost entirely, locked into prolonged periods of heat or cold. The oceans would respond first. Ice melt in polar regions would accelerate during periods of extreme tilt, raising sea levels unevenly. When the tilt shifted again, ice might begin to reform, locking water back into glaciers and destabilizing coastlines in the opposite direction. These swings would strain ecosystems already operating near their limits. Human societies would feel this as a loss of predictability. Planting calendars would stop matching reality. Monsoons would weaken or arrive late. Droughts would persist where rainfall once returned reliably. Migration would increase, not as a sudden wave, but as a steady pressure pushing populations away from newly hostile climates. What makes this scenario especially dangerous is its subtlety. There's no single disaster to respond to, no rebuilding phase after the damage is done. Instead, there is a slow erosion of trust in the environment. People would still look up and see the moon. They would still mark months. But the seasons would no longer behave as promised. Ancient cultures tied the moon to order for a reason. It regulated time not just in the sky, but on Earth itself. When stories warned of the moon being weakened or stolen, they were really warnings about losing rhythm, about the world slipping out of sync. Science supports that intuition. Simulations show that without a strong lunar stabilizer, Earth's tilt could vary wildly over geological timescales. In extreme cases, polar regions could face direct sunlight for extended periods, while equatorial regions plunge into long, dim winters. The planet would still be habitable, but unevenly and unpredictably. Civilization thrives on narrow margins. Predictable seasons, stable coastlines, reliable water cycles. Loosen the moon's hold, and those margins begin to disappear. In the next segment, we'll move from climate to consciousness, examining how a changing moon would alter human perception, culture, and social stability, and why psychological disruption might arrive long before the physical systems fully collapse. Long before a changing moon breaks coastlines or seasons, it breaks something quieter: expectation. Human psychology is deeply entangled with celestial regularity. The moon is not just an object, it is a pattern. It returns when it should. It looks the way memory says it should. For thousands of years, it has been the most reliable clock humanity ever knew. When that clock begins to drift, even subtly, the effect is not merely scientific. It is cultural, emotional, and social. At first, people would argue about what they're seeing. The moon would seem a little larger some months, a little smaller others. Its path across the sky might feel unfamiliar, its rise times increasingly misaligned with traditional calendars. Astronomers would explain. Data would be published. Models would be updated. But explanation does not equal reassurance. Humans are pattern recognition machines. When a pattern that has held for millennia begins to wobble, the mind does not process that change calmly. It searches for meaning. Some would see danger. Others would see destiny. Old myths would be rediscovered and reinterpreted. New ones would emerge. The moon has always carried symbolic weight, governing madness, fertility, time, and fate across cultures. A visibly changing moon would reawaken those associations almost overnight. Social stress would not arrive as panic at first, but as fragmentation. Competing narratives would form around the same sky. Some would trust scientific institutions. Others would see denial or manipulation. The moon's behavior would become politicized, spiritualized, and monetized. Certainty would fracture. Sleep patterns would shift as well. The moon influences circadian rhythms more than people like to admit, especially in coastal and equatorial regions. Altered brightness, altered timing, altered tides, all of it feeds back into human biology. Chronic sleep disruption degrades judgment, increases aggression, and erodes social cohesion long before infrastructure fails. History shows that periods of environmental unpredictability often coincide with ideological extremism. When the world stops behaving as expected, people seek frameworks that promise certainty. A changing moon would provide a perfect canvas for that impulse. Movements would arise claiming special insight into lunar meaning or future behavior. Some would promise protection. Others would promise salvation. Few would encourage patience. Even art and language would change. The moon has always been a metaphor for constancy amid change. Poets trusted it. Lovers trusted it. Remove that symbolic stability, and the cultural vocabulary itself begins to shift. What replaces it is often darker, imagery of loss, betrayal, or impending reckoning. This psychological erosion matters because it precedes physical collapse. Societies do not fail when systems break. They fail when shared belief in stability dissolves. Infrastructure can be repaired. Crops can be replanted. But trust, once shaken at a planetary scale, is much harder to restore. Ancient civilizations recorded eclipses, comets, and unusual skies with dread because they understood something modern culture often forgets. The sky is part of the social contract. When it behaves, order feels possible. When it doesn't, everything else feels provisional. A moon that no longer behaves would sit in the sky like a question no one can answer quickly enough. In the next segment, we'll move from perception back to physics, exploring the most extreme outcomes. What happens if orbital disruption goes too far and the moon's path crosses from instability into outright danger, transforming from stabilizer to existential threat? Most discussions of a changing lunar orbit stop short of the unthinkable. They assume adjustment, not collapse. Drift, not disaster. But celestial mechanics allows for darker outcomes, scenarios where the moon's path crosses a threshold and stability gives way to outright danger. An orbit can be altered without being destroyed. But once certain limits are crossed, correction becomes unlikely. If resonance, external nudging, or cumulative internal feedback were to push the moon into a highly elongated orbit, Earth would no longer experience a single, familiar lunar distance. Instead, the moon would alternate between dangerous proximity and uneasy retreat. Each close approach would amplify gravitational stress across the planet, and each retreat would weaken the stabilizing forces that keep Earth predictable. At extreme perigee distances, tidal forces would become destructive rather than regulatory. Oceans would surge not just higher, but faster. The timing of tides would tighten, compressing hours of rise and fall into violent pulses. Coastal megacities would be unsustainable. Not flooded once, but repeatedly and unpredictably until abandonment became the only rational response. The planet's crust would suffer as well. Earth is not rigid, it flexes. Under intensified lunar gravity, that flexing would increase. Fault systems would experience cyclic loading far beyond historical norms. Earthquakes would cluster around close lunar passes, not randomly, but rhythmically. Volcanic systems could destabilize as magma responds to new pressure cycles, increasing the likelihood of synchronized eruptions across tectonic boundaries. In the most severe scenarios, the moon could approach close enough for tidal forces to begin stripping material, not dramatically, not in a spray of debris, but as subtle stress fractures along Earth's crust and upper mantle. Mountain ranges would not collapse overnight, but erosion and landslide rates would spike. Continental margins would weaken. The sky itself would change in unsettling ways. The moon would appear unnaturally large at close approach, dominating the night with a presence that feels wrong even to those who don't understand the physics. Its speed across the sky would subtly increase near perigee, breaking the illusion of celestial calm. People would feel watched not by intelligence, but by mass. More extreme still is the scenario astronomers rarely discuss publicly, not because it's impossible, but because it sits at the edge of plausibility. A sufficiently destabilized moon could enter a decaying orbit. Not an immediate collision, but a slow inward spiral. Each pass would shave orbital energy away through tidal dissipation, bringing the moon closer over geological or possibly historical timescales. This would not be a single apocalyptic moment. It would be a countdown measured in generations. Every century, tides would worsen. Every millennium, Earth would grow less stable. Humanity would inherit a problem it could neither solve nor escape. Cultures throughout history imagined the moon falling, not crashing but descending, drawn down by unseen forces. Those stories were dismissed as symbolic, but symbolism often traces the outline of real fear. The moon is large enough and close enough that its failure is not abstract. Science does not predict such a collapse in Earth's near future, but it does acknowledge that orbits are conditional. They are not promises. They persist only as long as the forces sustaining them remain within narrow bounds. If those bounds are exceeded, the moon stops being a companion and becomes a hazard. In the next and final segments, we'll step back from catastrophe and look at perspective, how science evaluates these risks realistically, how likely such scenarios truly are, and why understanding them matters even if they never come to pass. After walking through instability, resonance, and collapse, it's natural to ask the uncomfortable question: how close are we really? From a scientific standpoint, the honest answer is reassuring, but not dismissive. The Earth-Moon system is currently stable. Remarkably so. Its behavior is well measured, well modeled, and deeply constrained by physics. There is no known object on an imminent trajectory that threatens the moon's orbit. No hidden countdown. No silent intruder already bending the system toward disaster. And yet, science never deals in absolutes. What makes the moon's orbit feel permanent is not that it cannot change, but that the timescales involved are usually longer than human history. Most of the processes capable of altering it operate over tens of thousands to millions of years. That places them safely outside the horizon of immediate fear, but not outside relevance. Earth itself is proof that rare events matter. Asteroid impacts capable of reshaping life are uncommon, yet they have happened. Climate shifts driven by orbital mechanics unfold slowly, yet they have repeatedly transformed the biosphere. The moon drifting away from Earth is not hypothetical, it is happening right now. What scientists watch for are not catastrophes but deviations, small anomalies, unexpected accelerations, subtle mismatches between prediction and observation. These are the early warnings in celestial mechanics, the signs that a system may be entering a new regime. Modern astronomy is extraordinarily good at this kind of vigilance. The moon's position is tracked with millimeter precision. Earth's rotation is monitored down to fractions of a second. Even the wobble of the planet's axis is measured continuously. If something were beginning to influence the moon's orbit in a meaningful way, we would almost certainly notice long before the consequences reach the surface. But notice does not equal control. Unlike asteroids on collision courses, an orbital shift in the moon would not be something humanity could deflect or prevent. There's no plausible technology capable of pushing a body that massive back into place. Awareness would buy time, not solutions. This is where the cultural value of these scenarios becomes clear. The purpose of exploring them is not fear but humility. The moon feels eternal because it has outlasted every human institution that ever looked up at it. But eternity, in physics, is provisional. Understanding that fragility reframes our relationship with stability itself. Climate, coastline, seasons, even the length of a day, all of these feel fixed because they change slowly. When they change faster than adaptation allows, the result feels apocalyptic even if no single moment marks the transition. The moon reminds us that the most profound threats are not sudden. They are systemic. Ancient observers treated the sky with reverence not because they misunderstood it, but because they understood their dependence on it. Modern science has stripped away the myth, but not the dependency. We now know exactly how much rests on gravitational balance, orbital timing, and distance measured in tens of thousands of kilometers. The moon's orbit is not doomed, but neither is it sacred. In the final segment, we'll step back one last time, looking at why humanity is drawn to these scenarios, what a changing moon reveals about our place in cosmic systems, and why imagining the sky breaking is ultimately a way of understanding how fragile order itself really is. The idea of the moon's orbit changing unsettles us not because it is likely, but because it exposes something we prefer not to think about. The sky feels permanent. It feels like the one layer of reality that exists beyond history, beyond politics, beyond error. When we imagine that permanence failing, even in theory, we are forced to confront how conditional our sense of order really is. Science strips the moon of its mythology, but does not make it ordinary. It reveals a body locked into a precise gravitational agreement with Earth. Stable, yes, but only as long as the terms of that agreement are honored. Distance, mass, timing, and motion all matter. Change any one of them enough, and the outcome shifts. Not instantly, not theatrically, but decisively. What a changing moon teaches us is that apocalypse does not always arrive as destruction. Sometimes it arrives as drift, as systems moving just far enough out of alignment that the future no longer resembles the past. Coastlines migrate. Seasons stretch and compress. Cultural rhythms lose their anchor. Nothing explodes, yet everything becomes harder to sustain. This is why cultures across time have watched the moon so closely. Not out of superstition, but out of instinct. The moon was a reference point in a world full of uncertainty. It told people when to plant, when to travel, when to rest. It was a reassurance written in light. Even now, with satellites and atomic clocks, that reassurance hasn't entirely faded. Modern astronomy gives us something ancient cultures never had: context. We know how rare stability is. We know that planetary systems form in chaos, that orbits evolve, that even stars wander. The Earth-Moon system is not a default, it is a fortunate outcome. One that allowed life not just to exist, but to persist long enough to become reflective. Thinking seriously about a changing moon is not an exercise in fear. It is an exercise in scale. It reminds us that human timelines are short, that planetary systems are dynamic, and that survival has always depended on narrow windows of balance. Civilization did not arise because the universe is gentle. It arose because, for a while, the universe was predictable. That predictability is not owed to us. In this sense, the moon is a lesson hanging in plain sight. It is close enough to matter, massive enough to shape worlds, and quiet enough to be taken for granted. Imagining its orbit shifting is a way of imagining the limits of control, the boundaries of adaptation, and the difference between permanence and persistence. The sky has never promised us stability. It has only loaned it. And as long as the moon continues its slow, faithful passage overhead, that loan remains in good standing, reminding us, every night, that order is not guaranteed, only maintained.